I wanted to work through test one, just to show you my solutions to test one. Just a word of warning though. So for each problem on test one, there were multiple versions of that problem. So the exact version that I'll solve might not be the exact version that you solved, but they're basically the same problems, mostly with different numbers. And so I hope this is a good guide. Anyway, number one asked me to figure out the number of cubic feet that there are in 1 cubic inch. And I was told that there are 12 inches in 1 foot. I mean, I already knew there was 12 inches in 1 foot. So the number of cubic feet in 1 cubic inch, just imagine it. It's going to be a tiny fraction of 1. A cubic meter is this big. A cubic inch is this big. And so there's only going to be a small fraction of a cubic foot in a cubic inch. But let's work it out. So we're told basically that 1 inch equals 1/12 of a foot. So that's actually 0.0833 feet. So we want to know what is 1 cubic inch, something that's 1 inch by 1 inch by 1 inch, some volume that's 1 inch by 1 inch by 1 inch. And we want to know that in cubic feet. And so what we've got to do is we've cubed here the left-hand side. We're going to cube over here the right-hand side to find the number of corresponding cubic feet. And if you cube the number, 0.083, you get 5.8 times 10 to the minus 4. And cubing the units, that's cubic feet. And so our answer for this one is right here. That's the number of cubic feet in 1 cubic inch. Okay, so that was the first problem. Second problem. We're told that a car travels from rest to 60 miles per hour and then slows down and stops. Let's picture that. There's 2 stages of this journey for the car. There's a first stage where the car is speeding up and a second stage where the car is slowing down. And to be more specific, we start out at speed 0. We reach a speed of 60 miles per hour, and then the car slows down to rest again, 0. And we're asked to indicate the directions of the accelerations during these periods, the first period and the second period, if, on my picture here, the direction of the car is in the negative x direction. Now, the acceleration during the first stage of the trip is in the direction of motion. So this would be the acceleration, and that would be in the negative direction. It's pointing towards the right. The acceleration in the second stage of the journey, because the car's slowing down, that's opposite the car's motion. So that's in the positive x direction. And so in this problem, because it involves a car first speeding up, which is acceleration in the direction of motion, then slowing down, which is acceleration opposite the direction of motion, the initial acceleration is going to be negative, and the final acceleration is going to be positive. So this answer here. In question number 3, we're told we have 2 apples, A and B. Apple A weighs 5 newtons on the moon, and apple B weighs 5 newtons on Earth. And we got to compare their masses. So let's start with the fact that their weights are the same on the moon for apple A and on the Earth for apple B. So their weights are the same. Now their weights are their masses, mass of apple A, times the acceleration of gravity where it is, which is the moon. And that must equal the weight of apple B, which is its mass, times its acceleration of gravity where it is, which is on Earth. Now, we know that the gravitational acceleration on the moon is less than the gravitational acceleration on Earth, 6 times smaller. If the left-hand side and the right-hand side are going to be equal, that means that the mass of the apple on the moon must be greater than the mass of the apple on Earth, must be 6 times larger. And so the correct answer is that the mass of apple A must be larger than the mass of apple B, this guy here. In question 4, we're told that we've got an arrangement where we've got a block of mass 2m placed on a block of mass m that together are placed on a horizontal surface. And we've got to comment on the sizes of the normal forces that are experienced by that mass m that's in the middle of this sandwich between the mass 2m and the horizontal table. Let me just draw the arrangement. So here's the arrangement where we've got these 2 masses on a table, the heavier one on top, the lighter one on bottom. And we're asked to figure out the normal forces that are acting on the lighter mass m. Well, there's 2 normal forces due to the 2 surfaces, the surface below the tabletop and the surface above the heavier mass. And so let's just sketch those two normal forces. I'll start with the one from below. I'll draw the arrow starting at the base of mass m. So that normal force here, I'll just call it N, that must be supporting, that table is pushing on this mass m to support both it and the mass on top of it. So it must be that normal force is 3mg in order to stop those 2 masses falling through the table. So that's one normal force. The second normal force, I'll draw it starting on the upper surface. That's due to the contact between the smaller mass and the heavier mass. So the smaller mass must be pushing upwards with a normal force on the heavier mass with a force that's 2mg so that the heavier mass is supported. And by Newton's third law, action-reaction, then that heavier mass is pushing down with a normal force on the smaller mass that's also 2mg. So I'm going to call that m prime, it's the second normal force, and that must be 2mg. And so there's 2 normal forces that are acting on the smaller mass, on the top surface, on the bottom surface, from the tabletop, from the heavier mass, and the one that is larger is the upward force. That's 3 mg. The one that's smaller is the downward force. That's 2 mg. This is the correct answer. In question 5, we're told that we've got a truck carrying a crate that's attached to the truck's cab by a rope, and that the truck and the crate are accelerating with acceleration A. And we got to figure out the tension that's in the rope, given that the truck bed is frictionless. To do this, let me just draw the force diagram for the crate. So just sketch out the forces that are acting on the crate. So here's the crate, its mass is m. There's a downwards force of gravity that's acting on the crate. There's an upwards normal force that's supporting the crate. And then there's a tension force due to the cable or the rope that's acting on the crate. And this crate is accelerating from the left, is acceleration vector, from the left to the right. Now, what is that tension then? What is the size of the tension force? Well, it's the tension force that's actually providing the net force that causes the acceleration of the crate. So in this sketch, the weight downwards and the normal force upwards, they counteract each other. They're equal and opposite. The non-zero force on the crate that creates the acceleration of the crate is the tension force. And so by Newton's second law says that the sum of the forces acting on the crate will determine the acceleration of the crate. The sum of the forces, because the normal force and the weight cancel each other out, is simply the tension force. And that will be equal to mass times acceleration. And so the magnitude of the tension force is just ma. In problem number 6, we're told that a cyclist travels north at 7 meters per second for 60 seconds. Then, after pausing, travels east for 20 seconds at 15 meters per second. And we got to figure out the magnitude of the displacement for the entire trip. So let's see if we can do that. First thing I want to do is picture the trip on a little diagram. Here's the cyclist traveling north. Here's the cyclist traveling east. Here's the displacement corresponding to the entire trip. Now, let's call this displacement for the first stage d1. Let's call this displacement for the second stage d2. And this displacement is d for the entire trip. The displacement for the first portion of the trip will be the speed, velocity, times the length of time. So that's will be the length of this side, the distance along this side here. And if you multiply the 7 meters per second by the 60 seconds, that's 420 meters. And same sort of thing for the distance traveled in the second stage of the trip. It's the speed during the second stage times the time elapsed for the second stage. That's 15 meters per second times 20 seconds. That's 300 meters. Those two stages of the trip form a right angle triangle with the displacement for the trip. And the displacement is the hypotenuse. And so by Pythagoras' theorem, the length of the hypotenuse, the magnitude of the displacement, is going to be the square root of the sum of the squares of the two other sides of the triangle. So we've just got to take the square root of 420 meters squared plus 300 meters squared. And if you do that calculation, I won't write all the numbers in, that comes out to be 520 meters. And so this is 520 meters. The next question says, look at the position versus time graph and figure out the instantaneous velocity at 4.5 seconds. So 4.5 seconds, let me mark it, that's here. And we want to know the instantaneous velocity at that moment. Now, the key thing is that on a position versus time graph, velocity, instantaneous velocity, is the slope of the line that represents position versus time. So we want the slope at this point here. And we can get the slope by dividing the vertical change during this portion of the trip by the horizontal change during this portion of the trip, the vertical distance traveled by the time elapsed for that little stage of the trip. That will give us the slope. So V will equal this change in time, change in position divided by change in time. And for convenience, if I just take this time between 4 seconds and 5 seconds, and the distance traveled between 4 seconds and 5 seconds to find this slope, the distance traveled is positive 6 meters. The elapsed time is 1 second. And so that's 6 meters per second. Positive 6 meters per second is the answer to that one. Next question is question 8. And in question 8, we're told in component form, the velocity vector for a aircraft that's flying through the air. And we're told to figure out the angle of the velocity vector for the plane, the angle below the horizontal. So let me picture the velocity vector and the components. So this horizontal here, this is 300 meters per second. And this vertical here, this is 30 meters per second. So the components are towards the right, that's the plus sign here, and downwards, that's the minus sign here. And we want to figure out this angle below the horizontal that corresponds to the velocity vector. That's this vector here of the plane. Well, we can just use a little bit of trigonometry for that. That angle theta is the arctangent or inverse tangent of the ratio of the size of the opposite side of the triangle to the size of the adjacent side of the triangle. So the size of the opposite side of the triangle, that's the size of the opposite, that's 30 meters per second. And the size of the adjacent, that's 300 meters per second. And so if we divide 30 by 300 and take the inverse tangent, we get the angle, and that angle comes out to be 5.7 degrees. And so that's the answer to that problem, 5.7 degrees measured from the horizontal, below the horizontal. Question number 9 tells us that a ball is thrown vertically upwards and reaches a maximum height of 9 meters. We've got to calculate the initial speed of the ball. So let me make a picture of this. And on the picture, I'm going to write down all the things, all the quantities I know about the ball's motion. So here's the ball's trip, and we're told that it reaches a height of 9 meters. So that's the difference between the final and initial positions. We know, of course, the acceleration is downwards 9.8 meters per second squared under gravity. We know at the top of the trip, at this moment, this final velocity is 0, and we're asked to figure out at the beginning of the trip what this initial velocity is. So to solve this one, we're going to use our equations of motion that apply to constant acceleration motion. And there's 3 of them, I'm sure you remember. And the one that we want to solve this problem of what is the initial velocity is this equation here. It relates the initial and final velocities to the acceleration and the displacement. So we know the final velocity is 0. We know the acceleration, we know the displacement. We can solve for V0. If I rearrange this, by moving the acceleration to the other side of the equation and taking the square root, I get this little expression for the initial velocity. And if we fill in the numbers, we've got -2 times an acceleration that itself is negative times the distance the ball rose into the air, 9 meters. The 2 minuses make a positive, so we can take the square root. And if you calculate this number, I got 13.3 meters per second. And so that's the solution to that one. In question number 10, we're told that we've got a basketball that is thrown between 2 players, and we're told the angle that it's thrown at above the horizontal, and we're told the speed that it's thrown at, and we got to figure out the separation between the 2 players. So let me just make a sketch of this problem. Here's the trip of the basketball. And on this, let me mark the things we know. So we know the initial angle theta is 30 degrees. We know the initial speed, V0, is 8 meters per second. And we're asked to figure out the distance traveled, the separation of the 2 players. That's what we call the range. And so this question is an example of using the range formula, that the range of a projectile depends on the speed that you throw the projectile at, V0, the angle above the horizontal that you throw the projectile at, the theta, and the acceleration of gravity. And we know V0, we know theta, we know the acceleration of gravity. We can plug all those numbers in. I won't write it all out plug in 8 meters per second for the speed, so we get 8 squared. Plug in 30 degrees for the angle, so we get the sine of 2 theta, sine of 60 degrees. Plug in the 9.8 meters per second squared for the acceleration of gravity, and you get a range that's about 5.65 meters. In question number 11, we're asked to consider a truck pulling a trailer, and the truck and the trailer have an acceleration of 0.4 meters per second squared. And we're asked to ignore friction on the trailer and figure out the tension in the cable that's pulling the trailer. So let me draw this situation. This is the trailer, 60 kilograms. This is the tension force in the cable that's pulling it. Of course, there's other forces on it. There's the weight of the trailer and a normal force supporting the trailer on the road. And we're asked to figure out this tension. Well, the normal force and the weight cancel each other out. It's the tension that is actually providing the acceleration of the trailer, and it's providing it according to Newton's second law, which says that the sum of the forces, which in this case will just be the tension force, as N and W cancel, equal mass times acceleration. And so all we've got to do in this problem, knowing the mass is 60 kilograms, knowing the acceleration is 0.4 meters per second squared, to figure out the tension is to take the product of those two to find the tension force. The tension force is 24 newtons in this case. Okay, the final question, final problem, is the fully worked out problem, where you submitted a PDF or a JPEG. And so let's solve this problem. In this problem, we're imagining a cart that's being pulled from left to right, from right to left across the floor by a person that's exerting a force. And we've got to figure out the normal force and the frictional force that act on this cart. So let's see if we can do that. So the first thing I'm going to do, here's the cart. We know it's 18 kilograms. And then I'm going to add to this picture the forces that are acting on the cart. So one force obviously is the weight of the cart. And we know that because we know the mass. So if you calculate the weight, the corresponding weight, that's 176 newtons. Then there's the applied force that's acting on the cart. We also know that that's 25 newtons in strength, and we know its direction is 50 degrees above the horizontal. And then there's the unknown forces that we're asked to figure out. There's the normal force, so we want to calculate that. And there's a frictional force that's opposing the motion. We want to calculate that. And a key point is in this problem that the velocity of the cart is constant. If the velocity is constant, i.e. if there's no acceleration, that means that the sum of the forces that act on the cart must equal 0. And so that's the situation in here, and that's how we're going to solve this problem. Now, the way we're going to solve for the two forces, the frictional force and the normal force, is to consider the horizontal and vertical components of all the forces. So let's start horizontally. The sum of the horizontal forces, that must be 0. And so what horizontal forces are there? Well, there's a component of the pull that's exerted on the cart towards the left, and then there's a frictional force towards the right. So that component is the horizontal side of this right angle triangle. So that's a portion of the 25 newtons that's acting towards the left. That's why it's got a minus sign. And then there's the frictional force that's acting towards the right. And those mess that up to 0. That tells us, right, that the frictional force is actually equal in size to the pull times cosine of 50 degrees. And if I fill in the numbers, 25 newtons and the cosine of 50 degrees, I get 16.1 newtons as the frictional force. Now I can do the same thing, same idea, for the vertical direction. In the vertical direction, the sum of the forces must be 0 because the object's in equilibrium. In this case, it's slightly more complicated, so that there's weight downwards, there's normal force upwards, and then there's the vertical component of the applied pull that's also upwards. So that would be F sine 50 degrees. But those three contributions must add up to 0. And so similarly, that means that if we want the normal force, it must be equal to the weight minus less this contribution of the pull. And since we know the weight, 176 newtons, we know the pull is 25 newtons, and we know this angle. If you fill in all those numbers, I got 160.0 newtons for the normal force. It is not 176 newtons because the pull on the cart is helping support the cart against gravity.